you are welcome to this session. It is session 2 of Unit 6. In this session, we are going to look at percentage of iron or iron oxide in samples of iron salts and rocks. Let's look at our objective. By the end of this session, you should be able to determine the percentage of iron or iron oxide in samples of iron salts and rocks. Let's move on. So determination of percentage of iron or iron oxide in samples of iron salts and rocks. A is a solution obtained after dissolving 4.00 grams of a powdered rock sample containing iron 2 oxide in excess dilute sulfuric acid, filtering off the insoluble material and making it up to 1 cubic decimeters. B is potassium permanganate solution of unknown concentration. C is 0.05 mole per decimeter cube sodium oxalate. The instruction is to put B into the burette B, which is the potassium permanganate of unknown concentration, into the burette and perform the following exercises. Pipette 10 cubic centimeters of C, the sodium oxalate, into a conical flask. Add 10 cubic centimeters of bench dilute sulfuric acid. Warm the resulting solution to about 80 degrees Celsius and titrate the hot solution with B. Pipette 25 cubic centimeters of A into conical flask. Add 5 cubic centimeters of bench dilute sulfuric acid. Ensure sufficient acidity and titrate the resulting mixture with A. Before we proceed, we need to draw something out of here, because usually with titration problems, if you understand it, the calculation becomes easier and simple. We are much interested in solution A, and so we are using B to find A. However, we don't know the concentration of B, so we can't do that. To be able to do that, we need another solution which can react with B. Then we can, through that solution of known concentration, find that of B. If we know the concentration of B, then now we can proceed to that of A. So we are going to look at a titration between B and C, convert the concentration here with the volume of C into moles. Then we will look at the reaction between B and C to find the corresponding moles of the potassium permanganate. Then, when we know the moles, with the volume of B used, we can find the concentration. So, once we get the concentration, we can move on to look at the relation between A and B. Then, we proceed. I hope it is very clear. So, we are expecting two equations. One is between B and C, and then another one is between B and A. Alright. Okay, so the equations are even provided here. This one is the one between B and C, the potassium permanganate of unknown concentration, and then the oxalate. Then we'll move on to between B and A. So we are asked to find the concentration of B, potassium permanganate in B, in mole per dm cube. And once we know that, we can find that of the ions and the iron percentage of iron oxide. Alright, so and then we will also explain why excess acid is recommended in titrations involving potassium permanganate. We are to take the average volume of potassium permanganate that reacted with the 10 cubic centimeters of C to be 20 cubic centimeters, and that of the potassium permanganate that reacted with A to be 26.00 cubic centimeters. Alright, so as we have been doing, we will do it here also. We go to the oxalate. That is where we can find concentration, and that is the part that will make it easier for us. Okay, so the concentration was given as 0.05 moles per dm cubed. That means that 1000 cubic centimeters contains 0.05 moles. Now, out of this, in the process, they used 10 cubic centimeters of the oxalate. So, if 1000 contains 0.05, then that 10 cubic centimeters that was fetched will contain how many moles? It will contain 10 times 0.05 divided by 1000. And that gives us 0.0005 moles of the oxalate. Now this is the volume, the 10 cubic centimeters is the volume that reacted with the potassium, with the volume of potassium permanganate. So the moles here are the moles that reacted with the moles of the potassium permanganate. So we need to know the agreement between the two of them, between the permanganate and then the oxalate. From this balanced equation, the mole ratio of oxalate to the permanganate is 5:2. It means that for every 5 moles of the oxalate, 2 moles of potassium, the permanganate ion is required. This is a redox reaction. Okay, so if 5 is equal to 2, then 0.0005 moles of the oxalate will require 2/5 times 0.0005 moles of the permanganate. So when we work this out, our answer is 0.0002 moles. So this is the moles of the permanganate that reacted. However, we were asked to find the concentration of the permanganate. This is the moles in 20 cubic centimeters. So we need to find the moles in 1000 cubic centimeters, and that will be our concentration. So to do that, we say that if 20 is equal to 0.0002, then 1000 will be equal to, if we put x there, you cross multiply and make x the subject, we are going to have this relation, which is 1000 times 0.0002 divided by 20, and that gives us 0.01 mole per decimeter cube of the permanganate. Alright, if this one was given to us in the question, we wouldn't have bothered ourselves. We would have just proceeded from here to find that of the A. But since it wasn't given, we had to find. Now that we have found it, we can now convert this one into moles, considering the volume of this that was used in the titration against A. So if we get the corresponding moles, we can do the mole ratio now, and then we get to the A. So we take it again from here and interpret it. Now, out of this 1000 cubic centimeters containing 0.01, it was 26 out of it that was used in the titration against A. So in our interpretation, we say 1000 cubic centimeters of the permanganate ion contains 0.01 moles of the permanganate ions. If 1000 is equal to 0.01, then that 26 cubic centimeters that was used will contain 26 times 0.01 divided by 1000. When we do this, we are going to get 0.00026 moles of the permanganate ion. So this is the number of moles of the permanganate ions that reacted with components of A. And so from there we can look at a reaction that occurred in the titration of B against A. In that titration, this is what happened. Iron was oxidized from iron 2 plus to iron 3 plus, whilst the permanganate was reduced. From this balanced reaction equation, 1 mole of the permanganate ion required or reacted with 5 moles of the iron ions. So if 1 mole is equal to 5 moles of the iron ions, then 0, that's moles of the permanganate, that's 0.0026 moles of the permanganate will require 5 times 0.00026 moles of the iron ions. Okay, and when we do this multiplication, we have this as the number of moles of the iron. Alright, but remember, since the volume of the permanganate reacted with 26 cubic centimeters of the iron ions, it means that this number of moles is the moles that were present, or that was present in that 25 cubic centimeters. Alright, in finding concentration, we need to use this volume with the moles to find the moles in dm cubed. We interpret this as if 25 cubic centimeters of the iron ions contains 0.0013 moles, then 1000 cubic centimeters will contain 1000 times 0.0013 over 25, and we get 0.052 moles in 1 dm cube of the solution. And this is the concentration of the iron. The next is to find the percentage of the iron oxide in the solution. To do that, we need molar mass. We have found concentration, and so we can use mass concentration formula to find the mass concentration of the iron oxide. Once we know that, then we can divide that mass over the total mass multiplied by 100. In so doing, we have rho, or mass concentration, to be amount concentration times molar mass. The amount concentration we found as 0.052 moles per cubic decimeters. So when we multiply it by the molar mass, we are going to get 3.74 grams per cubic decimeters. With a volume of 1 dm cube, the mass is 3.74. So if we want to know the percentage of, or percentage by mass of, the iron oxide in the solution, we divide that 3.74 by the total mass times 100%, and that gives us 93.5%. So we are done with that task. And the last part was why we needed to use excess acid. Excess acid ensures that the reaction goes from permanganate ion to the manganese ion. That is, the permanganate ion or the manganese here is reduced to Mn2+, and so the essence of the excess acid. My good friends, we are ending the session here with this self-assessment question. Once again, please try it. Try and solve it. We will meet again in the next session.